In this section, we're going to be discussing quantum mechanics. We'll take a quick look at wave-particle duality of matter. We're going to then look at the mathematical description of electrons in an atom and how that relates to something we're going to call wave functions or orbitals. And then we'll look at the 4 quantum numbers that come out of all this mathematics. And I'm going to do this in 2 video sections because it's quite long. In the early 20th century, a scientist named de Broglie argued that if electromagnetic radiation, light waves, can have both wave character and particle-like character, why can't an electron, which we commonly think of as a particle because it has mass, why can't it exhibit wave-like character? So in his view, if an electron is viewed as a circling wave now around the nucleus, we can actually introduce wavelengths to those integer numbers that was defined by Bohr, and that these wavelengths must fit into that Bohr orbital there. So he just added wavelengths to that model. That wasn't quite right, but it actually started the debate and started other scientists thinking about how we could mathematically introduce wave-like character into the movement or nature of electrons. So de Broglie's theory, could somebody actually demonstrate this? 2 scientists, Davison and Germer, they actually demonstrated experimentally that electrons can exhibit wave-like behavior by actually doing that sort of classical double slit experiment that we use in light. So they took a double slit, and then instead of a light source, they took an electron source, and what they observed is these interference pattern of electrons, these bright lines and these dark lines. So in other words, what they showed is that this interference pattern for electrons is strikingly similar to the interference patterns for light. In other words, we have wave-like character of electrons. A number of scientists followed up on this with a lot of math in order to model this wave-like nature of electrons. Eventually, the wave-like nature of electrons around a nucleus or an atom. A few other scientists that were important in this development of this new wave model or quantum mechanics were Heisenberg. Heisenberg's uncertainty principle said that it is fundamentally impossible to determine both the position and the momentum of an electron. We only know where it probably is. It's most likely here. And he came up with a mathematical equation for that. Another scientist named Schrdinger, probably the most famous one in relation to quantum mechanics, he actually determined a probability equation for electrons, where he actually modeled electrons as 3-dimensional stationary waves with nodes on them. This is actually where H in his equation is actually a Hamiltonian operator. For those of you that have taken differential equations, you're probably familiar with this. And this new symbol here is actually a wave function of the electron. After Schrödinger developed his equation, Max Born theorized that electrons are still particles, and so the waves represented by his new symbol psi here are not just waves, but instead are complex probability functions. So then he took the square of psi, of Schrödinger's equation, where the square of the magnitude of a wave function describes the probability of a particle now being present near a certain location in space with respect to the nucleus of an atom, or what we commonly call today as orbitals. So let's do that math, okay? Let's look at the math that Heisenberg, Schrödinger, and Max Planck all. It's actually kind of complicated, and it takes up a lot more pages than that. Here's all this ... It's actually kind of fun to take physical chemistry and actually solve Schrödinger's equations. And so mathematically now, We're just calculating the probability of locating an electron in a region of space around the nucleus. And that's sort of represented here. So if I take all this math, and this math says that probably the electron is located most likely right here, and it's a little less likely as I move away from the nucleus to be located out here. Scientists then came up with something what they call the 95% boundary, where it's 95% probable that the electron is somewhere within this sphere, and let's call that the orbit now. Okay, so Schrödinger's work, along with many other scientists, is generally referred to now as quantum mechanics. It's these orbits that are defined by probabilities now that we're going to look at for the rest of this section of the chapter. So I look at the good old Bohr model. My electrons are located in one of these orbitals that surround the nucleus. If I look at the quantum mechanical model and I solve all the math, I don't get spherical orbits all the time. I get some spherical orbits, and I get some of these dumbbell-shaped orbits. These are all probability orbits now. My electrons around an atom are either probably in this sphere, or at higher energy levels, they're probably in this pink sphere. And if I go to higher energy orbitals now, they're probably located in one of these dumbbell-like looking orbits. So in the Bohr model, I have quantum numbers of 1, 2, 3, 4, 5 as I move further and further away from the nucleus. The same is true here. When I'm close to the nucleus, I have a spherical orbit now. It's a three-dimensional orbit where my number is 1. We're going to call this a 1s orbit for spherical. As I move further away from the nucleus, I have another spherical orbit that I'm going to call n equal 2, or my 2s orbital. As I go further and further away from the nucleus, I now end up with these dumbbell-shaped orbitals, which we're going to call p orbitals now. So even though I have just 1, 2, 3 orbits here, they have different shapes. So in my 1 orbit here, as represented in the Bohr model, I only have spherical orbits. If I go out to the 2 orbit in my Bohr model and go out to my 2 orbit in my quantum mechanical model, I have both spherical and dumbbell-shaped orbits here. In fact, I have 3 dumbbell orbitals in my n equals 2 shell. I have a 2px, a 2py, and a 2pz, and those just represent the coordinates in which they're oriented, in the x direction, y coordinate, or the z axis. Chemists often go back and forth between these two models to explain different aspects of chemistry, and so we're going to do that throughout organic chemistry. Sometimes we'll use the Bohr model when it suits us, and sometimes we'll use the quantum mechanical model when it does a better job. Let's now take a closer look at the quantum mechanical model. The quantum mechanical model specifies the probability of finding an electron in a three-dimensional space around the nucleus. That three-dimensional space can be a sphere, it could be a dumbbell, or it can be some other space. It's defined by the mathematics. It's defined by solving Schrödinger's equation. There are 4 quantum numbers that are actually come out of all that mathematics, and let's review those quickly here, and then we'll talk about each of them in a little more detail. There is the first quantum number represented by n, and that is what we call the principal quantum number, and that actually specifies the shell. And that shell is very similar to the shells that we see in the Bohr model, 1, 2, 3, 4, 5, etc. There is a second quantum number which we call L, which is the angular quantum number. That specifies a subshell within that shell, and it's the shape, whether it's a sphere, whether it's a dumbbell, or some other shape. There's also a third quantum number called the magnetic quantum number, defined as m sub L, which specifies the orientation of the orbital in space. And a fourth quantum number called m sub s, which is the spin quantum number, which specifies the two possible states that the electron can actually occupy within one of these orbitals within the shell itself. So the first three quantum numbers define the space where an electron is most likely to be. And let's look at those. Let's start off with the 1s level, where my principal quantum number is 1, my angular quantum number is L, and that's an S in this case. The S means spherical. So I have a 1s orbital. It's in the first shell and it's spherical. If I go out to the next shell, I have several different subshells. Let's first look at the first one, which is represented by this sort of orange-pink sphere here. It has a principal quantum number of 2, and it has an angular momentum quantum number of s, so it's spherical. It's in the second shell, and it's spherical here. Also within that second shell, I have 3 other subshells. I have 3 p orbitals. So in this case, all 3 of these, the 2px, the 2py, and the 2pz, they're part of the principal quantum number 2 shell. But in this case, they have a different angular momentum, and these are going to be dumbbell shaped. They're my p orbitals. And they're going to have a different magnetic quantum number. One's going to be oriented in the x direction, one's going to be oriented in the y direction, and one's going to be oriented in the z direction. Now the fourth quantum number, that just defines the motion of the electron. It turns out electrons can spin, and so we're going to add that fourth quantum number here in just a second. But it does not define a shape, it just defines which direction the electron is spinning. Let's look at the principal quantum number, and let's start by looking at the Bohr model to explain that. If I look at hydrogen, we sort of have drawn 5 different energy levels around hydrogen that the electrons can occupy. And in the ground state, that electron sits down here in the n equals 1 level. So in the Bohr model, I have n equals 1, 2, 3, 4, 5, and so forth. We typically haven't drawn more than 5 or 6 so far, but in fact there are many other levels. And here is actually, based on the mathematics, how many electrons I can put in each level. In quantum number n equal to 1, I can put 2 electrons. If n equals 2, I can put 8 electrons. If n equals 3, I can put 18, and so forth. If I get up to n equals 7, I can put 98 electrons in there. And that's a direct consequence of solving Schrödinger's equations for quantum mechanics. If I look at the second quantum number, small sub l, or angular quantum number, we represent those by S, P, D, or F, and that tells us the shape of the orbital. So these shapes are represented by 3-dimensional regions where the electrons are most likely to be found. So if L equals 1, or S, that's going to be a spherical orbital. If L equals 1, or P, that's going to be a dumbbell-shaped orbital. If L equals 2, that's going to be a d orbital, and it has 5 different shapes that are shown here. They're a little more complicated. If I look at L equals 3, that's going to be an f orbital, and you can see my mathematical probabilities or shapes become very complicated in this case. So there are certain distances from the nucleus at which the probability density of finding an electron located is actually going to be equal to 0. That's going to be called a radial node. So we're sort of now relating that standing wave and nodes to my quantum mechanical nodes. Notice between this dumbbell shape here and my px orbital, there's a point right in the middle here where I have 0 probability of the electron ever being. That's going to be a node. And you can see nodes throughout these different descriptions of the different orbitals depending on the angular quantum number. If we look at the spherical orbits, or the s orbitals, those also have nodes, but in this case they're actually spherical nodes. Sometimes we call these a node or a nodal plane. So here in the 2s orbital, notice that I have a nodal sphere right here, and I have a nodal point here in the middle. If I look at the 3s orbital, I also tend to have nodes in this case that just happen to be spheres instead of points. So we have nodes in all of these different orbitals, whether they be 2p or 2s orbitals or 3p or 3p orbitals. If we look a little closer at a p orbital, we notice that it actually has two lobes of high probability. I have this brown lobe here and this yellow lobe here, and it's separated by a node passing through the nucleus. A node is defined as a point or a sphere where the probability of finding an electron is 0. So how can I have a probability of an electron either being on this side of the lobe or being on this side? How can I go between those two lobes? Mathematically, it's impossible, but we sort of then represent these sort of as a wave function, which allows us to pass through from one side to the other side. Okay, so all orbitals have nodes. S orbitals have spherical nodes, p orbitals, d orbitals, and f orbitals have more complex nodes. We can actually expand the Bohr model of the atom and expand it to include the second quantum number. So here I look at the first 5 shells as defined by the Bohr model. To actually expand that to include the second quantum number, or the angular quantum number, I just expand that to include more subshells. So if I take a closer look at that, I just take in n equals 1, I have one subshell, and it's S. I look at n equals 2, now I have 2 subshells, both the spherical and the dumbbell-shaped ones. If I look at n equals 3, I have both an S, 3 P's, and I have 5 D subshells. If I look at n equals 4, I have my S orbitals, my P subshells, my D subshells, and my 7 F subshells. So the Bohr model is still useful when I'm trying to explain some of the properties of atoms. When I combine that with sort of the quantum mechanical model, I just expand that to include subshells now. My third quantum number, the magnetic quantum number, m sub L, depends on the value of L. So if I have L equals 0, I can only have a spherical shaped shell in there in one orientation. If L equals 1, I could have 3 magnetic quantum numbers, either X, Y, or Z. So we have 3 subshells now. These subshells are actually called degenerate because they all contain the same energy. A px subshell has the same energy as a py, has the same energy as a pz. So my px, my py, and pz are all of the same energy. If L equals 2, then I have 5 magnetic quantum numbers. I have my dx squared minus y squared, my dxy, my dz squared, my dyz, and my dxy. Those are just nomenclature. Notice that the shape of those dumbbells are more complicated now. If L equals 3, it even becomes more complicated, and the names for those also becomes more complicated. These subscripts down here are related to the mathematics as we solve the Schrodinger equations. If we look at the final quantum number now, that just describes the intrinsic spin or the rotation of the electron. And I can only have 2 spins. I can either have a plus 1/2 or a minus 1/2 spin. We can sort of relate this to either, if I look at a magnetic field, I'm either spinning in the same direction of the magnetic field or I'm spinning in the opposite direction of the magnetic field. This has ramifications for putting electrons in the different shells, and we're going to review that right now. So let's look at all the quantum numbers and all the quantum shapes put into one big table here. Notice that for each shell, each primary quantum number, I have an S-shaped orbital. Once I get down to quantum shell number 2, I have both x and p orbitals. If I get down to quantum shell 3, I got s, p, and d. Once I get down into the transition metals and the intertransition metals, I got all kinds of different shaped orbitals. So I now include both my spherical, my p-shaped, my d-shaped, and my L-shaped orbitals. And this is just a representation of the probability where electrons are most likely found. So let's review all that. My principal quantum number, we're going to symbolize that by n. It's got integer values, 1, 2, 3, or 4. And we typically discuss that as the shell or the energy of the orbital. When we talk about the angular momentum quantum number, we represent that by the symbol L. And my allowed values are S, P, D, and F. And that tells me the shape of the orbital itself. The magnetic quantum number, represented by m sub L, that tells me the orientation. For the p orbitals, it's x, y, or z. For the d and f, it's a little more complicated, but that relates to the subshell orientation. And finally, my fourth quantum number, m sub s, it tells us a little bit about the electron spin direction in a magnetic field. It can either be plus 1/2 or it can be minus 1/2. All these quantum states or numbers can be combined to create a complete energy profile for the electrons orbiting about an atom. And that's what we're going to look at